series resonating circuit in which you'll see the variation of R, XL, XC, Z and I with respect to frequency. Now we know that V equals to IR or V equals to IZ, where Z equals to R plus J XL minus XC and XL equals to L, XC equals to 1 by omega C, and where omega equals to 2 pi of. Let us consider R, XL, XC, Z, I and X, where X is the reactance, which is nothing but XL minus XC along the y-axis, and we'll consider omega along the x-axis. R is independent of omega and it is a positive value, so R will stay constant. R. XL is a positive value. When omega equals to 0, XL equals to 0. When omega equals to, we have one more term, that is omega naught, which is nothing but resonating frequency. At resonance, XL equals to XC. Until here, as omega naught increases, the XL is going to increase. XL will become infinity when omega is infinity. This is our XL. When omega naught is 0, X equals to infinity and X is negative value. And at omega naught, X equals to XL. This omega increases, Xc value decreases from the infinity. And Xc is going to become 0 when omega is equals to infinity. Reactance X will start at infinity. Omega equals to omega naught. These are omega naught. This is Xc. This is going to increase as the XL increases. So this is X. Z is a combination of R plus J X. At omega naught equals to 0, that is Z will be at positive infinity, and it is going to decrease as this term is going to increase. It will become Z equals to R. Z is at infinity. Resonance frequency, Z equals to R. At infinity, Z equals to infinity. Z. From this equation, current I is inversely proportional to Z. This is our I. Two frequencies, that is F1 and F2, below and above the resonant frequency, have been identified and represented the 2 points of intersection of the current frequency curves at 1 by root 2 I naught. This is our I naught value. This is I naught by root 2, or RMS value is here. From these 2 points, we need to draw a line. This is F1 and this is F2. At this point, I equals to I naught by root 2 and V equals to V by root 2. Then power P at F1 equals to 1 by 2 I naught V naught. Half power point. F1 and F2 are also known as half power points, where F1 is the lower half power point, F2 is the higher half power point. This is the diagram which shows the relation between R, XL, XC, X, Z, I with respect to frequency or omega, where XL is the inductive reactance, XC is the capacitive reactance, X is the reactance, Z is the impedance. Q factor of the series resonating circuit. Q factor or quality factor is defined as the ratio of voltage across the inductor or capacitor to the applied voltage. Let V is the applied voltage, Vc is the voltage across capacitor, and VL is the voltage across inductor. Then quality factor Q is given by Vc by V or VL by V. Consider each separately. Q equals to VL by V, which equals to I naught XL divided by I naught R, that equals to XL by R, where XL is omega naught L divided by R at resonance. For coil, Q equals to Vc by V, that equals to I naught Xc divided by I naught into R, which equals to Xc by R, that equals to 1 by omega naught Cr. For capacitor. Now, from this 2, we can write VL equals to omega naught L by R multiplied by V. This is nothing but Q factor into V. Similarly, from this and this, Vc equals to 1 by omega naught Cr into V. that is VC equals to Q factor into V. Q factor is equals to, from this, omega naught L by R, where omega naught is nothing but resonant frequency, or 1 by root of LC multiplied by L by R, which equals to 1 by R square root of L by C. Similarly, from this, Q equals to 1 by omega naught, we are replacing with the root LC, CR, 1 by R root L by C. Q factor or quality factor, Q equals to 1 by R square root of L by C. Bandwidth and its relation with Q. The frequency band within the limits of lower and upper half power frequencies is called bandwidth. At half power frequencies, the net reactance of the series resonating circuit is R, that R equals to plus or minus XL minus XC plus or minus reactance X. This value at F1 frequency, at a lower half power frequency, the net circuit reactance is negative since the XC is dominating. And at F2, that is upper half power frequency, the net circuit reactance is positive where XL is dominating. And this can be represented omega 2L minus omega 2C is equals to R from this statement, and omega 1L minus omega 1C equals to minus R from this statement. This equation A and B. Now adding A and B equations, we'll be getting omega 2 plus omega 1 of L minus 1 by C of 1 by omega 2 plus 1 by omega 1 equals to 0. Omega 2 plus omega 1 of L equals to 1 by C, and LCM is omega 2, omega 1, omega 1 plus omega 2. Omega 2, omega 1 equals to 1 by LC. C. Now, subtracting B from A. Omega 2 minus omega 1 of L plus 1 by C of 1 by omega 1 minus 1 by omega 2 equals to 2R. Omega 2 minus omega 1 of L plus 1 by C. The LCM is omega 1, omega 2, where omega 2 minus omega 1 will be here, equals to 2R. Let this be equation number D. Dividing D with L. Omega 2 minus omega 1, L by L gets cancelled, plus 1 by LC, and omega 2 minus omega 1 divided by omega 1, and omega 2 is nothing but 1 by LC, equals to 2R by L. Now, omega 2 minus omega 1 2 times is equals to 2 times R by L. Omega 2 minus omega 1 equals to R by L. Let this be equation number 1. And we know that the Q factor Q is given by omega naught L by R, from which L by R equals to Q factor divided by omega naught. Substituting this in equation number 1, you will be getting omega 2 minus omega 1 equals to L by R equal to Q by omega naught. Here R by L is there, so omega naught by Q, from which Q equals to omega naught divided by omega 2 minus omega 1. This is in angular frequencies. Now let us change them into frequencies, that is F naught divided by F2 minus F1, where F naught is the resonant frequency. Q factor Q equals to resonant frequency divided by F2 minus F1 is nothing but bandwidth. Bandwidth, resonant frequency. The relation between Q and bandwidth is this. Selectivity and bandwidth. The selectivity of resonating circuit is defined as the ratio of resonant frequency to the bandwidth. Bandwidth, which is nothing but omega 2 minus omega 1, which equals to R by L, or F2 minus F1, which equals to R by L. The series resonating circuit's bandwidth is nothing but R by L. The selectivity is given by F naught divided by F2 minus F1, which is nothing but Q factor again, or resonant frequency divided by bandwidth. The frequencies F1 and F2 are also called 3 dB points, as the current ratios I1 by I0 is at F1, this is at F0. In dBs can be expressed as dB is equals to 20 log I1 by I0 to the base 10. Now 20 log to the base 10. I1 is nothing but 1 by root 2 of I0 divided by I0. Or simply you can write 20 log to the base 10 of 1 by root 2, which is nothing but 0.707. If you calculate this, we get a minus 3. That is, I1 is lower than I0 by 3 dB. Similarly, F1 is lower than F0 by 3 dB. The power dissipated at F1 or F2 will be half of the power dissipation. So half of the power dissipation, that is P at F1, is given by I1 square of R, which equals to I0 divided by root 2 square of R, which is I0 square by R by 2, which is the power P0 divided by 2. Even you calculate at frequency F2, you are going to get the same thing than P F2.